In this video, we're going to do the integral test and P-series. In the integral test, if f is positive, continuous, and decreasing for x greater than or equal to 1, and a sub n equals f of x, then the series a sub n and the integral of f of x either both converge or they both diverge. If the series converges to s, then the remainder r sub n equals s, the actual answer minus the partial sum, is bounded by 0 to the integral. So what this is saying is this is the maximum error we're going to have. And since the function is positive, continuous, and decreasing, we know that the sum is going to be bigger than 0, mainly because it's positive. In our example, we want to determine whether the following series converges or diverges. So we're going to look and we're going to see if this series converges by looking at the integral from 1 to infinity of really x over x squared plus 1 dx. Well, that's an improper integral, and so to do an improper integral, we're going to take the limit as b approaches infinity of the integral 1 to b of x over x squared plus 1 dx. Well, we do this integral by using u substitution. We let u equal x squared plus 1, so du equals 2x dx, and so we have 1/2 du equals x dx. Now we can change our limits of integration. If we put b in for x, we have b squared plus 1, and if we put 1 in for x squared plus 1, we have 1 squared plus 1, which equals 2. So now we have the limit. I'm going to go way over to the left. Limit as b approaches infinity of the integral from 2 to b squared plus 1 of now 1 over u, but we have a 1/2 in front of that now, is equal to the limit as b approaches infinity of 1/2 natural log absolute value of u evaluated from 2 to b squared plus 1. So that's the limit as b approaches infinity of 1/2 times the natural log of the absolute value of b squared plus 1 minus natural log of 2. And if we have b approaching infinity in here, that's just going to go to infinity. So this whole limit goes to infinity. Well, the integral diverges. So since the integral diverges, the series diverges by the integral test. And that's the answer that we're looking for. In the next example, we're going to take the limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1 dx. That's equal to the limit as b approaches infinity of, the integral of 1 over x squared plus 1, that's inverse tangent. So inverse tangent of x evaluated from 1 to b, which is equal to the limit as b approaches infinity of the inverse tangent of b minus the inverse tangent of 1. Well, the inverse tangent of infinity, if we look at the graph of inverse tangent, we have negative pi over 2 here, we have pi over 2 here, and this is inverse tangent. So as we're approaching infinity, the inverse tangent is approaching pi over 2. So this becomes pi over 2 minus, and the inverse tangent of 1 is pi over 4. Pi over 4 has a tangent that is 1, which is equal to 2 pi over 4 minus pi over 4, which is equal to pi over 4. Now the integral converges to pi over 4, so that means the series converges. So series converges by the integral test. Now that doesn't mean that the series converges to pi over 4. It just means that it simply converges. We don't know what it converges to. We'd have to show that in a different manner. In our next example, we're asked to approximate the sum of the convergent series by using 6 terms, include an estimate of the maximum error for your approximation. So the first 6 terms would be 1 over 1 to the 4th plus 1 over 2 to the 4th, which would be 16, plus 1 over 3 to the 4th, which would be 81. 4 to the 4th is 256, and 5 to the 4th is 625. So that's the first 5. I need the last one. I'm going to grab my calculator and get that value. So we have 1, 2, 3, 4, 5, the first 6 terms. Now we're going to use this to, approximate the sum. We're going to use this to approximate the sum or approximation. So the estimate is 1.0811, and we are asked to find the maximum error. And the maximum error, if we look back on the previous page, is the integral from n to infinity of f of x. So we're going to take the limit as b approaches infinity of the integral from 6 to b of 1 over x to the 4th. This is equal to the limit as b approaches infinity of, well, let's see, 1 over x to the 4th is x to the negative 4. We're going to add 1 to the power. That makes it x to the negative 3 and divide by negative 3. So we have negative x to the 3rd. Oh, nope. So we have negative 1 over 3x to the 3rd evaluated from 6 to b, which is equal to the limit as b approaches infinity of negative 1 over 3b to the 3rd minus, actually plus because it's minus negative, 1 over 3 times 6 to the 3rd. Now if we take the limit as b approaches infinity, that is going to be infinity, then it ends up being 0. So this is equal to 1 over 3 times 6 to the 3rd, 0.00154. Next is a p-series test, and it says a series of the form, sigma notation, n equals 1 to infinity of 1 over n to the p equals 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, and so on. This is called a p-series where p is a positive constant. So p is not a variable in this. P is going to be some value. For p equals 1, this series right here, in other words 1 plus 1/2 plus 1/3 plus 1/4, keep on going, is called the harmonic series. What values of p would cause that series to converge or to diverge? And we're going to look at when p is 1. So if p was 1, we'd have the series n equals 1 to the infinity over just 1 to the n. Now we're going to use the integral test to see if this converges or diverges as b approaches infinity of the integral from 1 to b of 1 over x dx, which is equal to the limit as b approaches infinity of the natural log of the absolute value of x evaluated from 1 to b, which is equal to the limit as b approaches infinity of natural log of b minus natural log of 1. Now this is going to just keep approaching infinity, so this is infinity and the series diverges. So if p is 1, this series is going to diverge. Let's see if p equals 1.1. So we have n equals 1 to infinity of 1 over n to the 1.1. We're going to find if this series converges in the exact same manner. So we're going to have the limit as b approaches infinity, integral of 1 to b of 1 over x to the 1.1 dx. Well, this is really x to the negative 1.1. So when we take the integral, we add 1 to the power. We get x to the negative 0.1. And then we divide by negative 0.1. So this is the limit as n approaches infinity of, this is really 1 over negative 0.1 x to the 0.1. And we're evaluating that from 1 to b. So we have the limit as n approaches infinity of 1 over negative 0.1 b to the 0.1 minus negative 1 over 0.1 times 1 to the 0.1. Well, now this part is going to go to 0. So we have 0 plus 1 over 0.1 times 1 to the 0.1. And whatever decimal value that is, it's just saying that this series converges. So the series converges. The lesson here is that if the p is bigger than 1, the series is going to actually converge. Now let's look if the series, or if p is less than 1. In this case, it's 0.9. So we have n equals 1 to infinity of 1 over the n to the 0.9. Well, we're going to see if this converges or diverges by the integral test. So we have the limit as b approaches infinity, integral of 1 to b of 1 over x to the 0.9 dx. Well, this is really x to the negative 0.9. We add 1 when we take the integral. So this is x to the 0.1 divided by 0.1. Now we have the limit as n approaches infinity of x to the 0.1 over 0.1 evaluated from 1 to b. Well, now b is going to be in the numerator, which is going to cause this to go to infinity, and it will diverge. So we have b to the 0.1 over 0.1 minus 1 to the 0.1 over 0.1. Now that is going to go to infinity, so the series diverges. So when we use the p-series test, we're going to compare the power to 1. If it's equal to 1, it's going to diverge. If the p is less than 1, it'll also diverge. The only time the p-series will converge is if the p is greater than 1. So we'll sum that up here with the p-series test. If p is equal to 1, the series diverges. If p is less than 1, the series diverges. If p is greater than 1, the series converges. So now if we look at the first example, we have n equals 1 to infinity of 1 over n times the square root of n. This is the same as writing n equals 1 to infinity of 1 over n times n to the 1/2, which is the same as 1 over n to the 3/2. In this case, p is greater than 1, so the series converges by the p-series test. Pretty simple test, pretty straightforward. Limit comparison test. It says suppose a sub n is greater than 0 and b sub n is greater than 0. And the limit of a sub n over b sub n equals some value, where L is both finite, so in other words a number, and it must be positive. If all these conditions are met, then the two series, each of them, either they both converge or they both diverge together. So let's determine whether the following converge or diverge. Here we have 1 over 3n squared minus 4n plus 5. We're going to compare that to 1 over n squared. And by the p-series test, this converges, because p would be greater than 1. So now we have to take the limit of a sub n. This is a sub n right here. This is the b sub n that I chose to compare it to. So we have a sub n, 1 over 3n squared minus 4n plus 5. This is as n approaches infinity, over 1 over n squared. Now we need to get rid of the complex fraction, so we can multiply the top and bottom by n squared. That's going to be equal to the limit as n approaches infinity of n squared over 3n squared minus 4n plus 5. Well, that's equal to 1/3. 1/3 is both finite and it's positive. Now, since b sub n converged, our original series converges by the limit comparison test. Let's look at the next one. I'm going to compare this one to just 1 over n. Really, it's the leading terms. Well, since p is 1, then this one diverges. Now I'm going to take the limit as n approaches infinity of n to the 4th plus 10 over 4 n to the 5th minus n to the 3rd plus 7 over, there's the a sub n that was given. I chose this to be the b sub n, over 1 over n. Now it's a complex fraction. We're going to multiply the top and bottom by n, so we get the limit as n approaches infinity of n to the 5th plus 10n all over 4n to the 5th minus n to the 3rd plus 7. Now this is like ending behavior. You could do L'Hopital's rule a whole bunch of times if you wanted. But this equals 1/4. 1/4 is both positive and finite. So since this series diverges, our original series also diverges by the limit comparison test. In our last example, I'm going to compare this one to 1 over n to the 3rd. And by the p-series test, this converges because p is greater than 1. So this one converges, and then we go through the same process. We have the limit as n approaches infinity of 1 over n to the 3rd minus 2. There's the a sub n. Here's the b sub n that I chose, 1 over n to the 3rd. Multiply the top and bottom by n to the 3rd. We get limit as n approaches infinity of n to the 3rd over n to the 3rd minus 2, which is 1. 1 is finite and positive. So our series converges by limit comparison tests. Limit comparison test. We have next a comparison of series, so the direct comparison test. If a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0, if the series with b sub n converges and a sub n is between 0 and b, so this one is converging, and it's greater than a, it's kind of forcing this one to converge as well. In number 2, if a sub n diverges and a is between 0 and b again, since this one is converging, in other words going off to infinity, and this one is bigger, it's forcing that one to converge or diverge. Excuse me, this one is diverging, not converging. It's diverging, shooting off to infinity, forcing that one to go to infinity as well since it's bigger. Determine whether the following converge or diverge. So we're going to compare this to 1 over n to the 3rd. Now, let's pick some value for n. Let's say it's 2. If n was 2, this would be 1/8, and this one would be 1/9. And certainly 1/9 is less than 1/8. Now, if we can show that this one converges, it's going to force the other one to converge as well. And by the p-series test, 3 is bigger than 1, so this one is converging. So our original one, our original series, since it's less than the one we compared it to, our series is converging by direct comparison. Test. In letter B, I'm going to compare this to 1 over 3 to the n. Well, let's pick a value for n. If n was 2, this would be 1/9. And if I plug 2 in for the other one, it'd be 1/11. And certainly 1/11 is less than 1/9. Now if I can show that this converges and it's bigger, then the other one has to converge as well. So this is actually a geometric series where the first term is 1/3 and then r equals 1/3, which is actually less than 1. So 1 over 3 to the n converges by the geometric series test, so our series converges by direct comparison test. On the last one, we're going to compare this to just 1 over the square root of n. Well, let's say n was something nice. Let's say n was, well, it starts with 4. Might as well use that. This will be 1/2, and this one will be 1, 1. Because 2 minus 1 is 1. So our series is actually bigger than this one. So 1/2 is actually less than 1. Now, if we can show that this one diverges, we got it. And by the p-series test, the power is 1/2, which is less than 1. So this diverges by direct comparison test.